Hey everyone. So we're starting Chapter 6. Chapter 6 is actually the second half of our class. We're just going to talk a little bit in the next few videos about this new thing. But I kind of want to start, before I talk about it, by drawing a picture. This is time, let's say hours, and let's say this is a velocity graph, and these are miles per hour here, okay? Now, what can you say? Let's say that miles per hour. Let's say that's 70 miles per hour. Okay. And so my question here is, how far did I travel in those 2 hours? How far did I travel? What can I say about how far I went? Well, I traveled for 2 hours at 70 miles an hour. This was constant. And so what do I know? Well, I remember in middle school, they taught me about distance equals rate times time. Here's a time. Here's a rate. See those slopey units? Miles per something, miles per hour. So what if I take the rate, 70 miles per hour, and I multiply by 2 hours? The hours cancel, and I'm left with 140. And what are those units? They're miles. So this graph represents traveling 140 miles. Okay? And what I did was I found the area, right? It's length times width. It's 2 times 70. It's 2 hours times 70 miles per hour. And because I found that area, I feel like I can say something about, well, that's no longer a rate, is it? That's a distance traveled, a change in position, a displacement, if you will. Remember, we said the displacement was S of B minus S of A. That's our displacement. And it seems to be, that's what I find here when I do that area. Well, that's interesting because this is a velocity graph, and it's telling me about a change on the position graph. Well, this is kind of significant and hugely meaningful. So let's, how about this one? What if I have this graph? Can you tell me how far I traveled in 4 hours? Is it possible for me just to do 60 miles per hour times 4 hours and cancel those out to get 240 miles? Is that what I should be doing? No. This is me finding the area of a rectangle. I don't want that area, that rectangle, because I don't want to include that. So I could, in fact, find this big rectangle and subtract off that little triangle. Likewise, I could think about finding this rectangle and adding the area of this triangle. Or, I see a trapezoid here. And the formula for area of the trapezoid is 1/2 height, base 1, 4, plus base 2, 2. So I'm going to have 1/2 60 times 6, or 180. Now what about units? Well, this is miles per hour, and these are hours. And then the hours cancel, and again, I have miles. And this works, pretty nice. It's really, I can figure out displacement if I'm given a velocity graph. Now, remember, displacement is a change in position. So I'm actually using velocity to say something about velocity's antiderivative. Remember, s of t is position, s prime of t, we call that velocity. So what I'm suggesting here is I'm looking at this graph and I'm learning something about a change in position. When I find the area under the curve in this graph, I'm saying something about the change in position on this graph. I'm going to write that down. When I find area under that curve, I'm also finding a change in position with the antiderivative s of t. That's pretty powerful magic. No, really, it is. So what happens though, I mean, because when I think about that graph, you know, that kind of looks like this, and I'm imagining sort of like my trip to Phoenix. Yeah, we wouldn't drive 60 if we were on I-10. But, you know, starting from my driveway and going faster and faster at a constant rate, and then just traveling at 60 miles an hour for the rest of the time. So here I want to say the slope on velocity is a constant. No, this is slope on velocity. Oh, slope is a constant, yeah. And what is the slope of velocity? Well, that's also known as v prime, and we know it is acceleration. So I'm clearly accelerating, getting faster and faster and faster, and then I have a constant velocity, which means acceleration is 0. I'm not accelerating at all. But does that look like your trip to Phoenix? Or does your trip to Phoenix look more like, I don't know, you were driving through town, you got almost to the highway, oh, slow down, because this is still V, this is T. Oh my gosh, there was a light, and another light, and finally we got onto the highway. So how do you do that thing about finding the area under the curve here? And the answer is second semester calculus. But we're actually going to start that now. And we're going to say, well, I'd like to find the area here. And what I'm going to do is I'm going to split this up into some little slivers and try and find the area of each little sliver. Before you freak out, let's just, take a look at a problem. I'd say that v of t equals t squared. Just t squared. Okay, so I'm going to, and I'd like on 0 to 4. And we'll call these seconds, and we'll say that velocity is feet per second. Okay. So I make my graph. I know what a parabola looks like from 0 to 4. This is 4, plug that 4 in for t, 16. This over here is 0, 0. But I can also say something about, sometimes it's better to make the marks before you draw the curve. So this one is 4, and halfway would be 2, 1, and there's 3. So here's what I propose. I propose that we consider finding the area of each of these slivers. And when we used a rectangle, we said we would do length times width. Oh, but I'm a little confused. Am I supposed to draw that rectangle, which doesn't count this area, or am I supposed to be looking at this rectangle, which not only counts that missing stuff from the first one, but overcounts? Like, this isn't actually under the curve, right? So, yeah, that's kind of a problem. But let's consider it. Let's take each of those in turn. So, I've got my velocity graph. I'm going out to 4, 1, and 3. I'm thinking about these little slices. And I want to introduce the following notion. I want to think about doing all of these that start on the left side of the interval and come across. On the left side of the interval, on the left side of the interval, and on the left side of the interval and come across. So what I'm seeing here is I'm finding this area. And I'm acknowledging that that's an underestimate of the actual displacement, actual change in position. And we're going to call this, when we start on the left side of the interval, we're going to call that LRAM. And LRAM is left rectangular approximation method. And I'd say on almost every AP exam in the last many years, you had a problem that may have involved LRAM. Or, if instead of going to the left side of the interval, going up to the curve and coming back across, if instead we went to the right side of that interval, went up until we got to the curve and came across, we'd be finding that area. If we went to the right side of the interval and went up to the curve and came across, we'd be finding that area. If we went to the right side and went up to the curve and came across. And we can see here that this approach, by the way, this one is called RRAM. RRAM is right rectangular approximation method, where I start on the right side of the interval, go up to hit the curve, come back across, and down. Here's my rectangle. Okay? So let's calculate LRAM and RRAM on the interval from 0 to 4 using this function. Okay? So if I'm doing LRAM, I'm starting on the left-hand side. I want to find the area of each of these rectangles, and the rectangle for the first one seems to have a height of 0. The second rectangle still has a base of 1/2, but what about its height? Well, its height goes to here. The height on V at 1. So I think what I really need to do here is make a little table where I put in 0, 1, 2, 3, 4 for my times, and I check out my velocities, because these velocities, the outputs on this function, the y values on this function, are going to correspond to the various heights that I'm looking at. Okay? V of 0 is the height or velocity at 0. V of 1 is what happens when I plug a 1 into the v function, so I get 1. V of 2, well, I'm plugging in a 2. 2 squared is 4. V of 3, 3 squared is 9. And V of 4 is 16. All right, so if I'm thinking about LRAM, let's think about what LRAM needs. It needs this times the height at 0. Well, the height at 0 is 0. So I've got a width of 1 and a height of 0. Plus, here, what's the width? Well, the width is still 1, but now the height up to the curve, the height on V at 1 is 1. Plus that subinterval width of 1 times the height at 2. At 2, the velocity or height is 4. Plus, and now we come to our last rectangle, the subinterval width is still 1. And I go up to the curve and say, hey, what's the velocity at 3? The velocity at 3 is 9. And so I end up saying that the displacement, or LRAM, that left rectangular approximation method, gives me a value of 14. And what are the units here? Well, if this is feet per second, because these are the velocity numbers, feet per second, these are seconds. Time goes in, velocity comes out. So I'm thinking about multiplying seconds times feet per second. The seconds cancel, and I'm left with 19 feet. If units are presented in a problem, I should put units on my answer. If units aren't presented in my problem, don't worry about units. And we know that this 14 represents the approximate area under this curve here, 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 and here. And so we're definitely undercounting. We know in this situation, LRAM is an underestimate. No, sadly, sometimes LRAM is an overestimate. Sometimes, yeah, so don't go there yet. We will go there, but just not yet. So LRAM was 14. Well, let's take a look at what RRAM would look like. What happens if we start not on the left side of the interval, but we go over to the right side of the interval, and we use that height, that velocity. So the subinterval width is still 1, but instead of, like LRAM, using this side, I'm using this side, the velocity at 4. So I'm going to have 1 times 16 plus, for this rectangle, I'm going to the right side, I'm going up to the curve, and I'm taking this as the height. That's the height or velocity at 3, which is 9. I also know that that subinterval width, 3 minus 2, is 1. And here, for this rectangle, start on the right side, I go up to the curve, so I need the velocity or height at 2, which is 4. And the subinterval width from 1 to 2 is still 1. And finally, over here, for this rectangle, I go to the right side, I need the velocity at 1. The velocity at 1 is 1. And from 0 to 1, the subinterval width is 1. And again, I could pull out that subinterval width, because it's a constant here, and just add up all these heights. And what do I have? 20, 30. I get 30 as RRAM. RRAM is 30. And what I know is LRAM and RRAM aren't the exact area under the curve. I mean, how could you possibly get rectangles to get the area under the curve? And that's the big question we're going to be trying to answer. I know the actual area under the curve has to be between this number and this number. So, yeah, it seems like a wide disparity between values. Is there anything I could do to get these numbers closer to each other? What could I do to get closer to the actual value? Well, I can think of a couple, maybe even 3 or 4 methods of getting closer than this. One that I'd like to explore with you is where we take that same function, and this time, instead of thinking about, sorry, getting lost in drawing this not crappily. And here's my velocity, and that's equal to t squared, and we have a little table. But what if instead of these 4 subintervals, oh, by the way, remember how we were going from here to here, and we kept talking about this being a constant change? Well, I'm going to say that that change in x values, which in this problem is really a change in t values, that change can be found by doing b minus a over n, where n is the number of rectangles. Okay, so what I'm finding here is the subinterval width. This is my recipe for subinterval width, and it will in fact be periodically very important that I know that. And what's nice about subinterval width is, in this situation, subinterval width, when I take 4 minus 0 divided by 4, I get a subinterval width of 1. a constant subinterval width. And that allowed me in the last problem, where we had n equal to 4, so we went 4 minus 0 over 4, my subinterval width is 1. And that allowed me, remember, we had 1 times 0 plus 1 times 1 plus 1 times 4 plus 1 times 9. This was our LRAM. But look at all these subinterval widths. I pull out the subinterval widths, and I'm just looking at adding up the heights or y values on this graph. Because these are the heights of the rectangles times the subinterval width. When my subinterval width is a constant, I can always just do that constant times the sum of those y values. And if I'm looking at a table, 0, 1, 4, 9, I'm really talking about what's the change in this. That's my subinterval width. And I'm just going to add up these numbers. Okay? We didn't use this one because, remember, we started on the left side of that interval and we used the value at 3 rather than the value at 4. Okay, but we did use 4 for RRAM. Okay, so this little recipe, subinterval width is this. Well, I want to think about this situation. What happens, right? Remember, LRAM had given us 14, and RRAM had given us 30. My question was, how do I get these values closer to each other? What can I do? Well, here's what I think I can do is, how about instead of 4 rectangles, we have 8 rectangles? What if we have 8 rectangles here? So with 8 rectangles, I've got 0 and 4 still. This is 2, and there's 1, and there's 3. But now I want a 1/2, and a 3/2, and a 5/2, and 7/2. Still with the same function, velocity is still t squared. These are still 1, 0, 1, 4, 9, and 16. But now I need these heights as well, right? I need the height here at 1/2. I need the height here at 3/2. And so I'm going to find those by plugging these values into this function, t squared. So I'm going to square 1/2 times 1/2 is 1/4. And 3/2 times 3/2 is 9/4. 5/2 times 5/2 is 25/4. And 7/2 times 7/2 is going to be, and why is it 7/2 times 7/2? Because this is a squaring function. I'm plugging in a time and I'm squaring it. So I get 49/4 here. And maybe it would make sense to turn these into fractions whose denominator is 4. So this would be 16/4, and this would be 36/4, and that would be 64/4. Okay, wow, that's a lot of work. I must really want this approximation of the area under the curve. And sure, I can do that. Again, we've got a constant subinterval width from here to here, from here to here, from here to here. And what is that subinterval width? 4 minus 0, but this time, instead of having 4 rectangles, we've got 8. The number of rectangles for us in this problem is 8. And I'll say that in almost all, you're given the number, like you're told the number of subintervals to use. There are some occasions where you're asked to try and do something, and we'll come back and talk about what you do then in a little while. Okay, so let's think about doing, so 4 minus 0 over 8 was 4 over 8, or 1/2. And we see that the subinterval width really is 1/2. These values go up by 1/2. Okay, so what I'm looking at here, then is thinking, all right, I've got an interval of 1/2 times the height, and we're doing LRAM again. The height over here is still 0, plus 1/2 times the height over here, because I'm finding the area of the second one. The height at 1 is the height at 1. That's very weird. The height at 1 should be 4/4. Thank you. Do I need the height at 1? No, I'm doing LRAM. Sorry, let's start over. Clear your brain, clear your thought. LRAM. I start on the left side here at 0. The subinterval width is still 1/2, but the height here at 0 is 0. Now I'm doing the second rectangle here, and the width is still 1/2, but now the height is the height at not 1, but on the left side, 1/2. The height at 1/2 is 1/4. Plus, again, the subinterval width is 1/2, but now I need the height because I'm finding this area. My height here at 1 is 1 or 4/4. Okay, how many of these will I have? That's right, I'm going to have 8 of these, 1 for each of those rectangles. So I'm finding the area of these rectangles. And so what I notice here is I'm doing the subinterval width times that number, and the subinterval width times that number, and the subinterval width times that number, and I'm going to do the subinterval width times that number. So next I'm going to do the subinterval width, which is still 1/2, times the y value or height on the left side of that subinterval, 9/4, plus here I want the subinterval width, oh look, it's 1/2 again, times not this height, but the height on the left side of that rectangle, and that's going to be 16/4, plus the subinterval width, still 1/2, times the height not here, but on the left side of that rectangle, 25/4, plus the subinterval width here, which is 1/2, times the height not here, but over here at 36/4. And finally, this last rectangle, we still have a subinterval width of 1/2, but we don't use that height, we use this height, 49/4. Yeah, it's a little cumbersome using all those fractions. However, what do I have to do now? I have to add these values up. So I think I really want them to have a common denominator to make my life a little easier. You could also do some GCF factoring here. All of these terms have a 1/2 in common, also known as subinterval width. And what else do we have? Well, we've got all these heights. So 0 plus 1/4 plus 4/4 plus 9/4 plus 16/4 plus 25/4 plus 36/4 plus 49/4. But wait a minute, says you. Couldn't I also take out not only the subinterval width, but couldn't I also take out a 1/4 here? Of course you can. So we've got our 1/2 times that 1/4 we're taking out, and now we've got 0 plus 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. And the nifty thing here is that you see all these perfect squares, which makes entire sense because our outputs are all perfect squares. Fabulous. So what do I have here? Well, this is going to be 1/8. And here I've got 10 plus 20 is 30, 40, 55, 85, 91, 140. So I got 140 times 1/8, or 70 over 4, 35 over 2, or 17.5. Well, that's interesting. So now my LRAM is 17.5. Okay. What would RRAM look like? Well, the subinterval widths would all be the same, but if I'm doing RRAM, I don't want to start on the left side of the subinterval. I want to go to the right side of the subinterval. And so if I go to the right side of this subinterval and I use the height over here at 1/2, my setup is going to look a little different. And do we have 17? Let's make this the space, 17.5. Okay, so what's going to change here? Subinterval width times the velocity or height at the left side is now going to become subinterval width, what's the height at the right side? So instead of 0 here for this first rectangle, I'm going to use this value, 1/4. And on the second rectangle, I'm not going to use this height, I'm going to use this height, 4/4. And on the third rectangle, I'm not going to use this height, but instead I'm going to use this height, 9/4. And over here, I'm not going to use this height, I'm going to use this height because I'm going to the right side of that subinterval. And so on. 25, 36, 49, and finally 64. So my setup now is going to be, oh look, they all still have the 1/2. Oh look, they all still have the 1/8. So I'm going to factor out the 1/2. That represents our subinterval width. There's this convenience factor here of 1/4 that I'm going to pull out. And now I'm looking at 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. I really should make those closer together. All right, 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64. Okay? Notice, what's the difference between this RRAM and the LRAM we did? The LRAM had this, had 0 plus 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 as our sum. And what that means is, or what I see is, LRAM is using the y values from the y values at 0 to 3/2. See how we're stopping at that 49/4? That's our LRAM. LRAM uses all the heights except the last one. Whereas RRAM didn't use that first height. It used all these heights. And so RRAM is going to be all the heights except the first one. Now, I will say that while I don't quite yet know when LRAM is an underestimate or an overestimate without looking at the picture, or when RRAM is an underestimate or an overestimate without looking at a picture, what I can say is that LRAM will always, always, always be all the heights except the last one. And RRAM is always, always, always going to be all the heights except the first one. And so from a table problem, I can just add up all those heights. I mean, that's what this represents. I'm adding up all the heights from not the first one, but from there on. And in LRAM, I'm adding up all the heights from the first one, but I'm not doing the second one. Okay? So I actually find a table approach to this really fast by comparison, but you do have to build the table. All right, so we got LRAM was 17.5 when we increased the number of subinterval widths. What happens to our RRAM? Remember, originally, with only 4 subintervals, we had an RRAM of 30. So let's see what we get now. We've still got that 1/8, but now we're looking at adding up all of these. So I've got 20, 30, 55, 91, 140, plus 64 is 204. Okay, so does 8 go into 204? No, I don't think so. But I can take a 4 out of each of these, right? Yeah. So that's going to be 51 on top and 2 on the bottom, which is 25.5. 25.5. So what happened to our approximation of the area under the curve when we went from 4 subintervals to to 8 subintervals? And it may be useful for us to actually look at both of the graphs and see what we see. You know, in our original situation, with only 4 subintervals, we were looking at this being the discrepancy, or maybe this times 2-ish, not quite, because that's not a straight line. But we saw that LRAM was an underestimate, but check out, like, it's an underestimate by all this area. Well, now when I look up here, yeah, still an underestimate, but look, these are much tinier than these. And so I think what I'm saying is I can get closer to the actual area under the curve by getting LRAM and RRAM closer together. So if instead of 8 subintervals, I went with 16, or 256, or a million. Muhammad, I've never seen the AP exam have a problem like this that had you doing by hand more than 10. Generally, it's like 4 to 6. And so 8 is plenty for us to get this idea. 8 is a number that allows us to see, oh look, over here, when we only had 4 subintervals, this was 14. And when we had the RRAM for 4 subintervals, we had 30. Big gap between these numbers. Well, that gap got smaller because my number of subintervals got smaller, which means these areas got tinier. Okay? So what I'm really looking for is this place of convergence where L and R are the same number. Because when L and R are the same number, I'm feeling like I've got the area under the curve. Now, if we were in class, I'd attach your calculator to mine, and I'd give you this nifty program. And there's actually 2 of them that, you know, if you want this program, get it on Google. It's a TI program called RAM. There's another one called All Sums. And I actually like using that one a little more because it's got a little more information to it. And you can type these short programs. I've done it a number of times into my calculator. And these short programs, I don't know, half hour, hour to type it in. But then instead of n equal to 4 or 8, you could do something like n equals 10,000. And the calculator will compute that approximation for you. But I think we're going to skip that part right now. And instead, we're going to say one way to get a better approximation of the area under the curve was to make n get bigger. Bigger. The more rectangles, the closer we are to the rectangles, the closer we are to getting the actual area. You know, right now, all we're getting is a better approximation or estimate. You'll see these words a lot when we want you to be using RAM of the area under the curve. Okay, but guess what? Not only could we change the n value to get closer, we could also try a different approximation. We saw RRAM. That meant start on the right side of the interval, use the height at the right side times that subinterval width. We saw LRAM, which said let's start on the left side of the subinterval and use the height over there. Well, I'd like to offer a third option. 4, 2, 1, 3. Instead of starting on the left side and going up and getting the height and finding that area, instead of starting on the right side, going up to the curve and finding that area, I'm going to do this other thing. I'm going to go halfway across and pick up that height. Now, look what happens. I got a little overcounting here, and over here, I'm missing this area below. And while these are not equal triangles, They're definitely not triangles. This is a curve. They are close in area. And so by using this value in the middle for MRAM, I think I can get a little closer. Unfortunately, that means I have to find the y value at these places. I have to find the y value halfway across the subinterval. Halfway across, I go up, and I find the height there. Halfway across, I go up, and I find the height there. And again, I keep seeing, look, I'm overcounting a little, but I'm undercounting all this. I'm overcounting, but I'm also undercounting. So let's see what happens here. In fact, I want to just use n equals 4 here, just 4 subintervals. The subinterval width then, 4 minus 0 over 4 subintervals, is 1. So this is always going to be 1 in this problem. Many students, because they're now going and using these x values to find the heights, they think, oh, now my subinterval width is 1/2. No, no, no. Subinterval width is not 1/2 in this situation. It's still this whole rectangle. I'm just stopping halfway across that base to go and get my height. Okay, so what's the setup going to be for MRAM with n equals 4? Well, with n equals 4, I'm looking here and saying, no problem, I've got a subinterval width of 1 times the height at 1/2. Well, what was the height at 1/2? Well, 1/2 times 1/2 is 1/4. Plus, the subinterval width, again, is 1, times, what's the height halfway across the interval? What's the height at 3/2? 3/2 squared is 9/4. And then this rectangle here, I still see the subinterval width of 1, and now my height is not the height at the left side or the height at the right side, it's the height midway across that interval at 5/2, so I have 25/4. And finally, my fourth rectangle still has a subinterval width of 1, but if we stop halfway across and go up, 7/2 squared is 49/4. All right, again, I can pull out the subinterval width, right? That delta x equals 1. We can pull out a 1 from all of these. And they all happen to have a common denominator, so I could take out that 1/4. And now I'm left with 1 plus 9 plus... Why don't I have 16? Oh, right, because I don't have 4 either, or 36 either. Don't worry about that, because we're not stopping here or here. We're just going halfway across. Okay, so I've got 25 plus 49. Okay, this isn't 1/8 like it was when we were doing 8 subintervals. It's just 1/4. 4 subintervals are happening here. I've got 10 plus 25 is 35. 35, I'm now 75. I'm now 84. So I've got 84 times 1/4, which is 21. So when we think about LRAM being 17.5, and we think about RRAM, wasn't it 25.5 when n equals 8? And we know the actual area is somewhere between those two numbers? Wow. That's like almost spot in the middle of those numbers. So here's the thing. MRAM, it's a little more labor intensive, but I can get a pretty accurate area under the curve with half as many rectangles. And so maybe that work balances out. There are actually 2 other methods for approximating the area under the curve. We're going to look at one of those, the trapezoid sum. And the other one, Simpson's rule. Yeah, Simpson's rule shows up in second semester calculus. It's not something that we make use of, so I'm going to let you experience that on your own, though it's described in the textbook. And so I encourage you to take a look at that. All right, so how can I get more accurate estimate? I can increase the number of subintervals. Or I can change methods. Now, about the changing methods, so here's the thing. I don't change methods. I don't change methods because on the AP exam, they always tell me what I should use. And sometimes it's LRAM, and sometimes it's RRAM, and sometimes it's MRAM, and sometimes this value is this other one that we're going to talk about, trapezoid sum. And they don't say find LRAM, they say find a left Riemann sum. Named for Georg Riemann. He's got great, big, bushy mutton chops on his face. It's a hairstyle, a facial hairstyle. Georg was the one who said, hey, let's add up all the areas of rectangles, and so his name gets attached to that. You won't see LRAM on the AP exam. You'll see left Riemann sum. That's a synonym for LRAM. And likewise, you could have a right Riemann sum, and that's going to be our MRAM, or a middle Riemann sum, and that's going to be our MRAM. So my recommendation is that you practice these a little bit. And so the practice I think we should do is, why don't we take a different curve, like y equals square root of x, and see if we can approximate the area onto the curve. This is a different looking curve, isn't it? It looks like this. And so when I think about, again, from 0 to 4, 1, and 3. So now when I think about LRAM, oh wait, I want you to think about LRAM. I want you to try and find LRAM here, okay? So go find LRAM in this situation. Left rectangular approximation method, you're using the left side of the subinterval to draw that height instead of the right side of that subinterval. Okay? So pause the video, give it a try. I see here that my subinterval width is a constant 1. So I'm just going to pull out that constant, and I see that if I'm using the left side, I'm going to be using this y value, I'm going to be using this y value here, this y value here, this y value here. I'm not going to be using the last one. Remember, LRAM uses the first, but not the last. 1, square root of 2, square root of 3, and square root of 4 is 2. So LRAM uses these values. 0 plus 1 plus root 2 plus root 3. And RRAM still has the same subinterval width, but instead of using this first height, we'll use the last height. So I've got 1 plus root 2 plus root 3 plus 2. Okay, so what do we get? Well, I see here that if I add up 1 plus the square root of 2 plus the square root of 3, make sure I'm typing this into the calculator properly. Okay, 1 plus square root of 2 plus square root of 3 plus 0 is going to be LRAM 4.146. And RRAM, well, it's going to be adding up these numbers. I already added those to get this, plus 2. RRAM in this problem turns out to be 6.146. Okay? So, I think you should be comfortable determining LRAM and RRAM from a graph, given a function, right? We have to be given a function, from a graph or from a table. Okay? I know the actual area between these curves lies somewhere in between. Here's my LRAM, and here's my RRAM. Go to the right side, go to the right side, go to the right side, go to the right side. Okay? And so I'm going to be finding these areas. And these are clearly overestimates of the actual area. So I know somewhere in between. I could use MRAM, but what about doing this? What if I averaged L and RRAM? 4.LRAM plus RRAM divided by 2. Well, 4.146 plus 6.146 divided by 2 is going to be 5.146. Wow, you know, pretty smack dab in the middle. But we don't have a straight line here, we have curve. So I'm expecting that while this is close to the actual area, oh look, another method. We can average L and RRAM, but that's really labor intensive. I gotta find that one, I gotta find that one, and then I have to add them together and divide by 2. So while this is a very close approximation, yeah, well, so I run into this problem where it's a lot more work to try and do that thing. So I just wonder what the actual area under the curve is, not the approximation, but the actual area. And my calculator says that the actual area under the curve is 5.33333. Well, these are still a ways off. Damn, that got really close with only 4 subintervals. Okay, so we want to be thinking about, what we can do to get a more accurate area. I really think you should practice this a little more, I might actually say, why don't you do the 8 subintervals with this? You should probably actually also find MRAM here. It's still going to be a subinterval width of 1. In the next video, we'll look at situations where the subinterval width is not constant. But here, where the subinterval widths have always been something that we could choose, then, yep, I'm going to make subinterval width be b minus a over n. So that's why I'm getting this, because I'm looking at 0 to 4 as my a and b values. All right, so, what about this? Well, if I were thinking about MRAM and my 4 subintervals, the subinterval width is still 1 for each of these, but now I'm going halfway across, and I'm using that height. Halfway across, and using that height. Okay, 1 second while I let my wife know that coffee is imminent. Coffee is imminent. Let's see what we can do with this last piece of information. Okay, so this is 1/2, this is 3/2, this is 5/2, this is 7/2. So I'm going to use those heights, right? And those heights come from plugging values in there. So with MRAM, I'm looking at not at the height at 0, not at the height at 1, but the height at 1/2. Square root of 1/2. Not the height at 1, not the height at 2, but the height at halfway across. Square root of 3/2 plus not the height here or the height here, but the height halfway across. Square root of 5/2. And here, same. Not height here, but height here. And so square root of 7/2. So let's see what I get when I add up all of these. I'm going to have subinterval width times 1. So I'm just adding up these values. The square root of 1/2 plus the square root of 3/2 plus the square root of 5/2, not 5, but 5/2, plus the square root of 7/2. Did I type that in properly? Yes, I typed that in properly. And I get that MRAM is 5.384. Remember, the actual area under the curve was 5.333. And what was our average of M and R RAM? Wasn't it 5 point, sadly I can't go up and check, but I think it was 5.146. So yeah, that average is pretty good. MRAM is looking really good. And the actual is something that we're going to learn how to find in very short order. Approximations. Okay, you've got these approximations. I recommend trying LRAM, RRAM, and MRAM for 8 subintervals. Okay, and I will tell you that the actual, well, you already know the actual area under the curve. The actual area under the curve is 5.333 repeating. So see what happens when n equals 8. Give those a try. The last thing I want to say about this is how do I know when LRAM is an underestimate or an overestimate? Okay? So in this situation, LRAM turned out to be an underestimate. And what about in this situation, like our parabola? Well, again, LRAM turned out to be an underestimate. So underestimate and overestimate doesn't seem to depend on concavity, but instead on whether or not my function is increasing or decreasing. So here, take a look. Decreasing. Decreasing. If I now consider LRAM here, I'm starting at the left side and going over, starting at the left side and going over, now LRAM is this big overestimate. And here too, with concave down, my LRAM is still an overestimate. Okay? So LRAM is an overestimate for a decreasing function, and LRAM is an underestimate for an increasing function. And likewise, RRAM turned out to be an overestimate for increasing function, and RRAM turned out to be an underestimate for a decreasing function. Of course, this then sort of begs the question, what if your function isn't always increasing or decreasing? And we also need to talk about a tangent line. Is my tangent approximation an underestimate or overestimate? We'll talk about that in due course. I look forward to seeing you in the next video. Take care, everyone.